Right, hello Year 9. So we've actually now finished this topic of energy. So next week, so that is on the Monday the 18th, I'm going to set you an end of topic test on energy. So we're going to be revising this lesson. So I'm going to go through a few of the key things that you need to know, and then you are going to be left to do some of your own revision towards the end of the lesson. Okay, so first thing you need to do is I'd probably advise you to copy this up. Now, energy is always measured in the unit of joule, and as you can see from this, there are several ways in which you can work out energy. Okay, and we need to identify what they mean. So, energy P stands for potential. Okay, so the potential energy, we need to know how we go about calculating that. Now, when it's talking about potential energy, it's talking about gravitational potential energy. So for those of you that can recall, to calculate the gravitational potential energy, you need to know the mass times the gravity times the height. Okay, so mass times gravity times height will equal gravitational potential energy. And then, of course, you can triangle that up. So if I just quickly get rid of that for a second. Okay, hopefully you all remember your equation triangles. Now, most equation triangles only have two factors in them, but also this one has three. Okay, so in this case, it would be, oops, sorry, forgive me, like this. Mass, gravity times height equals gravitational potential energy. Okay, so say for example you were asked to work out the height, you'd simply cover it up and it'd be gravitational potential energy there in joules divided by mass times gravity will give you the height. Or say for example you wanted to know what the mass of the object was there. Okay, it'd be gravitational potential energy divided by gravity times height, and that would give you the mass. Okay, so we know how to use the triangles. Okay, so that's that one. Energy can be calculated by Q divided by V. Now, don't worry too much about this one. You haven't come across it yet. Q is charge, V is voltage. So you're actually going to come across that one next topic. So I'm not going to pay too much attention to that one at this time. Okay, but other forms of energy that you need to be familiar with. K. K is kinetic energy, and the way we go about calculating that, if for those of you can remember, is this: half mv squared. If I can just type that in there, yeah. Okay. Okay. So what that means is, if we want to know how much kinetic energy, how much movement energy an object has, let's just say you had something that weighed 100 kilograms, okay? We put in firstly half. Now half, always put in as 0.5, then times, say, 100 kilograms. Now say it was moving at 5 meters per second, you'd do 5 times 5, okay, which is obviously 25. So it'd be 0.5 half times mass 100 times 5 times 5, because it was moving at 5 meters per second, and that will give you the kinetic energy. That's just an example though. Okay. E, elastic potential energy. Okay, so this one is actually very similar to this one. It's half Ke squared. Okay, I think, hang on a minute, what's K? And we did do this. K is the spring constant. Now, in the exam, you'd always refer to it as a spring constant. Basically, it's an object's stretchiness. Okay, so what you would do for this one is, say, for example, you had an object which stretches, say, by 1 meter, like a giant spring. Okay, you'd do half times its spring constant in newtons per kilogram times its extension squared. So say if it becomes extended by 1 meter, it'd be 1 times 1, which would obviously be 1. Okay, but whatever number it gives you. Okay, so that one, actually, you don't need to remember. It's going to appear on your equation sheet, but always useful to just sort of be familiar with it. Another way of working out energy is power times time. So this one really relates to sort of machines and objects, but basically it can relate to anything. So you need to, basically, energy can be worked out by multiplying the power by the time. Now the power is how quickly one kind of energy is transferred to another. So say, for example, in a car, chemical energy, which is the petrol, maybe gets transferred to kinetic energy, which is movement. And maybe that takes 10 seconds. Okay, so what we would do, say 1,000 joules of chemical energy in petrol gets transferred in 10 seconds. You do 1,000 times 10. So the energy is 10,000 joules. Okay, if you want to know the power, how quickly it gets transferred, you do how much energy you've got divided by time. Okay, so again, that's this one triangled up. And see, this one's only got 2 factors, whereas this one has 3. This is the one you really, really need to be familiar with. It looks complicated, but it's actually not too bad. Okay, this is specific heat capacity. Now, you remember before we closed the school, we did do one with metal blocks. You all had your metal blocks and you weighed them, and then you worked out how much energy was going into your metal blocks from the heaters that you attached. I'm hoping you'll remember that experiment. It looked a bit like this. Okay, you had your metal block, your thermometer sticking out, your heater stuck in. Well, that equation links to this, and it's called specific heat capacity, and that's C. C is the specific heat capacity, and that's an object's ability to absorb energy. Okay, and the way you work that out is energy divided by mass times temperature change. Okay, so once again, we can triangle this one up, and I'll just show you. Okay, so just to remind you, if I wanted to find out, say, for example, the specific heat capacity, or sorry, the energy to begin with, the little triangle means change, it's actually change in energy, but I just haven't included it, you don't need to. It'd be, I need to know the mass of the object, times by the specific heat capacity, times by the temperature change. That will give me the energy. But, as you know, because you've used these triangles, if you want to use them backwards, say, for example, I want to know the specific heat capacity, I cover it up, and what I would do is energy divided by mass times temperature change. Or if I wanted to know how much temperature had gone up by, I do energy divided by mass times specific heat capacity. Or of course, if I wanted to know the mass, I do energy divided by specific heat capacity times temperature change. So you can see how these triangles all link together. Okay, so the next thing, in the exam, they refer to energy as stores. Now, these are some of the types or stores of energy that you'll be familiar with. So thermal basically means kinetic, heat. Kinetic, that's movement energy. Gravitational potential energy. If you lift something up, it's got the potential to fall. Okay, so that is gravitational potential energy if it's just held there. Elastic potential energy. If you stretch an elastic band and hold it in the stretch position, it has potential to move. Chemical energy. Things like petrol is a chemical, and you can burn it and release that energy. Or food. Food is made up of chemicals. So if you eat, say, chocolate bar, you break down the chemicals and release the energy. Magnetic, electrostatic, and nuclear don't really need to know a great deal about. But energy is never used up, just transferred between stores and objects. Right, key thing, energy cannot be created or destroyed, only transferred between these stores. So say, for example, if you eat a chocolate bar, that's chemical energy. The energy isn't lost, the energy is used to keep your body warm, to allow you to move. you might climb up a ladder. That gives gravitational potential energy. Okay, there's lots of different ways in which this chemical energy can be transferred to these different sorts. Okay, these different stores, but it's never lost. Okay, sorry, it's never destroyed. So, for example, the thermal energy can dissipate out into the environment. It's still there. It's just so spread out we can't really use it. So, you'll hear something referred to as a system, just a fancy word for objects. So, for example, the water is the system. The heating element transfers energy, and heating adds energy to the water's thermal energy store. Okay, to its thermal energy store. So essentially, you might be asked, what happens to the kettle's thermal energy store when it's turned on? It goes up. Take, for example, a pair of colliding cars. The kinetic energy combined for the colliding vehicles is a system. So you think of that as a closed system. So an example might be, this would be a very higher order question. How fast is the ball moving when it hits the ground? Okay, well, let's just think about this for a moment. Okay, let's just give a couple of values here, and you can actually, it's probably a good idea to have this example as we go. Let's just say our ball weighs 2 kilograms. Okay, and the height that is lifted up is, say, 3 meters. Now, the question is, how fast is the ball moving as it hits the ground? Right, well, let's think about this. M is mass. Right, so we know the mass is 2 kilograms. We know the height is 3 meters. And there is something else that you're expected to know. Gravity in Earth is 9.8. Now, this is just one of those values that you are expected to know. Okay, it's just one of those things. Now, this, hopefully some of you realise, will give us gravitational potential energy. It won't really tell us anything about how the ball is moving yet, but let's actually work it out. So, just clear that for a minute. So, its mass is 2 times 9.8 times 3. Right, so 58.8 is how much gravitational potential energy there is. Now, this, let's just see what we know down here. Half mv squared. That gives us the kinetic energy. Now, we know that energy can't be created or destroyed. So whatever that is, it must be the same as the kinetic energy. So we just move that down there. Half is half, so that's fine. And the mass we already know is 2 kilograms because the mass of our ball. So now we've got everything we need. Okay, so once again, what we can do, just clear that, we do 58.8 divided by half times 2 equals, right, 235.2. Right, well, here's the problem. That's the velocity squared. So what we need to then do is square root that. So the square root, wherever my square root button is. Right, apologies for that. So in this case, the speed at which the ball is moving, I need to square root it. So it's 15.3 meters per second. Now that is a very complex example of how you would use your energy equations. Will you come across anything that complex? Not until your real exam in a couple of years, and probably only at the end of the higher paper. But I thought it was good to throw it in there. Okay, next thing, specific heat capacity. You will 100% need to know this required practical. Now you've done it, so you need to refer to this in your book. Okay, just went through it with you a few minutes ago, so hopefully you'll be familiar with this. I'm actually not going to spend a great deal of time on that. Right, energy can be dissipated, but never created or destroyed. Okay, only transferred. Now, conduction is the process by which vibrating particles transfer energy to their environment, to their neighboring particles. So what happens when an object gains energy, particles gain energy, is they vibrate. And as they vibrate, they transfer that energy to the neighboring particle. Now, a couple of things about this. Firstly, this happens well in solids and liquids because solids and liquids are dense, they're tightly packed together, and so therefore the energy can be distributed quite easily. Metals make exceptionally good conductors because they have delocalized or free electrons, and they're able to transfer energy much more efficiently than simply normal particles. Okay, a couple of other things you need to know. So we know about energy. We know the different stores that energy can have or the different forms it can take. We know that energy can't be created or destroyed. So you also need to recognize and explain the benefits and drawbacks of the different ways of generating electricity. So we've done this more recently. We've got wind turbines turning kinetic energy into electrical energy, solar, light energy into electrical energy. We've got tidal, so again, the kinetic energy, the movement of the water going in and out of this bay creates electrical energy. We've got gravitational potential energy, so all the water is held behind the dam, and as it falls through the dam, it turns turbines which generate electricity. So once again, it's gravitational potential to kinetic energy. Nuclear, okay, so again, we know how this works. Nuclear reactions turn water into steam. Steam has kinetic energy, and that's used to turn turbines, generate electricity. And then geothermal, it uses heat from under the ground. Okay, so you would be expected to know the benefits and drawbacks of, say, all these different kinds of ways of generating electricity. So, for example, coal, is it renewable? Your answer would simply be no. Pollution, yes. Carbon dioxide and sulfur dioxide. Reliable, yes. We know exactly how much we've got. Startup cost, moderate. Running cost, moderate. Locations can be put pretty much anywhere. Okay, so coal has both benefits and drawbacks. Okay, so what you could do is think about the benefits and drawbacks of each of the different ways of generating electricity. A certain example, wind turbines. One wind turbine, one nuclear power station can generate the same amount of electricity as 1,500. So you need 1,500 of these to generate the same electricity as just one of these. So again, you've got to think about the benefits and drawbacks of that. So the UK is trying to create more and more renewable electricity. Okay, and the use of renewables is limited by reliability, money, and politics. For example, if we switch to wind farms completely, what would we do on the days when it's very calm and there's virtually no wind? Okay, so we've got to think about how this works. Also, money, the cost of going green is a lot, and politics, we're often tied into deals with countries to export and import coal, oil, gas, things like that. So there's a lot of money and politics involved in how we generate our electricity. Right, efficiency. Now again, this is one that is often overlooked. Now if you have the purple revision guide already, use the bottom page 18, and there's a good section on storage heaters. But if you haven't yet got that, okay, don't worry, I'll post that up for you a bit later, but definitely have a look at that. This is one of the equations you do need. So remember, this line in your triangle is this line, which means useful goes at the top, total and efficiency go in the bottom. Okay, so you can work out the efficiency of any device, and basically efficiency is a measure of how much energy is wasted. Okay, so say for example a car, 1,000 joules of energy, of chemical energy from the petrol might go into it, but you might only get 300 joules of kinetic energy. What's happened to the other 700 joules? Well, mostly it's been lost as heat, a bit of sound. So the efficiency would only be 30%. Okay, so you've got to think about how you would work that out. Okay, but again, we've done quite a large section. That's all in your book. Right, so what I'm going to do is, for the remainder of the lesson, so you listen to me talk for about 20 minutes, so you've got about 25 minutes or so, but I'd suggest you do a bit more, is I want you to go back through your book and basically make sure you are familiar with everything that we have done so far on energy. Now, if you want, you can use page 23 of the Purple Revision Guide to help you answer the questions. If you can answer those questions, then you're probably in quite a good place for the test next week. So I'll post that up here in a moment. Okay, maybe try and do as many as you can. This is just for yourself. Okay, essentially, it's about you being comfortable with what you understand already about this topic. So, thinking about what you need to know, okay, just going back, you need to be clear about the different types of energy stores, so thermal, kinetic, gravitational, things like that. You need to know a few of the equations. You need to know about specific heat capacity. You need to know about power. Okay, power is quite a big one. Conduction, okay, and efficiency, and then finally the different ways in which we generate electricity, such as wind, geothermal, biofuels, hydroelectric, nuclear, all of that. Okay, so I'm going to post up some questions. However, I am essentially going to leave you to your own devices for the rest of the lesson to revise. Okay, so it should all be in your science book. Okay, if you get really stuck, you can use online resources like BBC Bitesize, whatever, anything like that. And then next lesson, there will be a test. The test will be about 45 minutes. And then what I'll do is I'll post up the answers afterwards. Okay, so use the time wisely. Obviously, you know how you revise best. Good luck.